Hey everyone, and welcome back. Today, we are diving into something really cool. A brand new paper that gives us a completely new way to see what's actually happening inside the AI models that are all around us. It's called Tensorlens, and honestly, it could completely change how we understand and even trust AI. So we all know transformers are the powerhouse behind, well, pretty much everything now, from ChatGPT to incredible image generators. But here's the billion-dollar question that keeps researchers up at night. How do they really work? It's what we call the black box problem, and it's one of the biggest hurdles we're facing in AI. Okay, so this diagram here should look super familiar if you've ever looked into how these models are built. This is the classic picture of a transformer block, right? You've got your self-attention module, some normalization, a feed-forward network. It's all stacked up nice and neat. It's a clean little picture, but as we're about to find out, it's not the whole story. Not even close.
And that's the real issue. Seeing it as just a stack of blocks is a massive oversimplification. It tells us the parts are there, but it tells us nothing about how information actually flows, mixes, and transforms across all these components and through dozens of layers. It's like having a list of car parts but no blueprint to see how they all connect to make the engine run.
This brings us to the main tool we've had for peeking inside, attention maps. For a while, they were the best thing we had. But the problem is, this tool has some really serious blind spots that give us, at best, a blurry, incomplete picture of what's going on.
Right, so think about it like this. Attention maps, on one hand, are kind of useful. They show us how one word is paying attention to other words, but only within a single little component, one attention head in one layer. But just look at everything they miss. The huge computations in the feed-forward networks, the normalizing effects of layer norm, the residual connections that carry information forward, and most importantly, how all of that snowballs across the entire model. And hey, don't just take my word for it. The authors of this paper nail it with this quote. For years, we've been stuck looking at these tiny, individual pieces, completely failing to see the big picture, the model's global, holistic behavior. We've been looking at the individual trees, and we've totally missed the forest.
So how do we fix this? How do we get out of this fragmented, piece-by-piece view? Well, this is where the big idea behind Tensorlens comes into play, and it is a really clever solution.
So the authors asked a really powerful what-if question. What if, instead of trying to stitch together all these tiny, blurry snapshots from different attention heads, we could just build one single, powerful lens? A lens that could see the entire model's computation from input to output all in one go.
And here it is. This is the core goal. The idea is to mathematically reframe the entire transformer. We're talking all the layers, all the parts, into a single thing called an input-dependent linear operator. Now, I know that sounds like a bit of a mouthful, but stick with me, because we're going to break down exactly what that means and why it's such a game changer.
Okay, so how in the world do they actually build this thing? Let's walk through the main idea here. And don't worry, we're going to focus on the intuition, not get bogged down in a ton of heavy math.
First up, let's demystify this term linear operator. Honestly, for what we're talking about, you can just think of it as a fancy, more powerful version of a matrix. It's a function that transforms data. It might stretch it or shrink it or rotate it, but it does it in a nice, predictable, straight line kind of way. It's a way to create a clean, linear approximation of all the messy, complex stuff happening inside the model.
And the second key term is high-order tensor. So we're all pretty used to vectors, which are just a list of numbers, and matrices, which are like a 2D spreadsheet. Well, a tensor just keeps adding more dimensions. A third-order tensor is like a cube of numbers, and a fourth-order tensor is like a row of those cubes. It sounds a little mind-bending, I know, but you need that complexity to capture the relationship between every single input and every single output. A simple matrix just doesn't have enough room for all that information.
And this visual just perfectly captures the whole idea. On the left, you've got our old friend, the step-by-step transformer block. And on the right, that's the Tensorlens view. That whole sequence of operations gets mathematically squished down into one single, unified object, that high-order tensor. It's a totally different way of thinking about what the model is doing.
So how do they build it? Well, it's pretty methodical. The researchers basically go through each part of the transformer, the self-attention, the layer norm, the feed-forward network, and they figure out the tensor for each one. Then they use some clever math to compose them, kind of like snapping together Lego bricks. They do this for every single block, and then they compose all the block tensors together until they're left with one single massive tensor that represents the entire model from start to finish. It's really an elegant bit of engineering.
All right, so
this is a beautiful idea on paper. It's mathematically elegant. But the real question is, does it actually work? Does this new tensor thingy give us a genuinely better, clearer picture of what the model is doing compared to the old methods?
To figure this out, they used a really smart experiment called an input perturbation test. The logic is simple. You use your tool, either Tensorlens or an old attention method, to rank which input tokens are the most important for the final answer. Then you start deleting the most important ones. Now, if your tool is accurate, the model's performance should just fall off a cliff right away, right?
And the results? Well, the results are pretty darn clear. This chart shows what happened with a vision transformer. The metric here, AUC, basically just means a higher score is better. It means the tool was better at finding the most critical inputs. And look at that. Tensorlens gets a score of 0.084. The best of the old methods, only 0.059. That's not a small bump. That is a massive leap in performance. It shows that this new lens is way more aligned with the model's actual logic.
So, the takeaway from the experiment is a resounding yes. This tensor isn't just a neat theory. It's empirically, provably, a much, much better stand-in for what the model is actually doing inside. Okay, so it works. It's better. But what does that actually mean for people in the field? For researchers, for engineers, what can we do now that we couldn't do before?
Well, this gives us a much stronger foundation for all kinds of interpretability work. First, it's just way more accurate because it actually includes everything, the feedforward networks, the layer norms, the whole shebang. Plus, the authors cleverly designed it to be a drop-in replacement, which means you can swap it into your existing tools without a total rewrite. And all of this creates a much better starting point for the really deep work of mechanistic interpretability, where we try to reverse engineer the actual algorithms these models are learning.
And here's maybe the best news of all, especially for the research community. The team made their code completely open source on GitHub. This means you, right now, can go download Tensorlens and start using this more powerful, unified lens on your own models for your own research questions.
So in the end, Tensorlens gives us a much clearer, much more powerful microscope to study what's going on inside these incredibly complex systems. And it leaves us with this huge, exciting question. Now that we can finally peer inside the black box with this newfound clarity, what should we be looking for? What incredible new secrets are just waiting to be discovered? And that's the next great challenge for all of us. Thanks for watching.